this lesson, we're going to be talking about maximum and minimum values of functions on an interval. The whole idea is that if we have some function on an interval, let's say from A to B, we're going to look at ways of finding the maximum or minimum values of a function on that interval. Now, for this example, we see that the minimum value occurs at an endpoint and the maximum value occurs at an endpoint. But that doesn't always have to be the case. If we have something that looks like this, we can see that the maximum value occurs here and the minimum value occurs here. So in this section, we're going to be looking at techniques of finding these maximum values of functions on an interval. That will lead us into some very interesting problems that we can solve later on in this section. Here are some examples of problems that involve maximum and minimum values, and they're called optimization problems. A definition. A function f has an absolute maximum or global maximum at c if f of c is greater than or equal to f of x for all x in the domain of f. If I have a function and I'm going to say the domain is from A to B, I can see I have a maximum value here at x equals c. And this value would be f of c. What this definition is saying is that if I choose any other value other than c on the interval from A to B, any other x value on this interval, let's say I chose this value right here, I can see that y value is less than f of c. If I chose this value over here, I can see that value, f of x of 2 sub 2, is less than f of c. And that's what this is indicating right here. If we have an absolute maximum, plugging in this value c will give me a number larger than any other value that I plug in on the interval a to b to the function. This number f of c is called the maximum value of the function on this domain. And likewise, if we have an absolute minimum value, same idea occurs. If we have this value c, we're on this interval a to b, this value f of c will be smaller than any other value that I plug into the function and evaluate. So this f of x sub 1, that would be larger, and any other value, I think I may have said smaller, but I meant larger, this value would be larger also. So any value of x we plug into the function will give us a larger value than the value of c being plugged into the function. So that gives us an absolute minimum value. The maximum and minimum values of f are called the extreme values of f. Determine the absolute maximum and minimum values of this function. We have a domain here of -5 to appears about 5.2, let's say. If we're looking for the absolute maximum It occurs here. When we indicate where an absolute minimum or maximum occurs, we give the x value. We say it occurs at x equals -5. Now the actual value would be 9. That's the maximum value. And that's what the problem is asking us to find. The absolute maximum value. So that would occur at x equals -5, but the value is 9. The absolute minimum, it appears this is approximately, let's say, 3.8. The absolute minimum occurs at x equals 3.8, and the value -7.8. Now we're going to look at a different type of maximum and minimum value. We've learned about absolute maximum and absolute minimum values on this interval from -5 to 5.2, but there are also what we call local maximum and local minimums. The way I like to describe local maxes and local minimums is the local minimums occur in the valleys. So right here, this would be considered a local minimum. And we can see another valley, so this would also be considered a local minimum. And notice, an absolute minimum can also be a local minimum. Now the hills, the highest point on the hill there, we call a local maximum. So we can see a local maximum, it appears, occurs at about -0.25. So these local maximum and minimums occur at our hills and valleys. And notice, we would not consider this a local maximum. It's not a hill. Local maximums and local minimums do not occur at the endpoints. So here we said this is a local minimum. This value here we said is a local maximum, the top of that hill. And then we said we had another local minimum where the absolute minimum occurs also. Now we do have another name for these. We call them local minimums or local maximums, or relative minimum, relative maximums. Definition: a function f has a local maximum at c if f of c is greater than or equal to f of x when x is near c. So that's why we were localizing these points around c. And also if f has a local minimum at c, then f of c is less than or equal to f of x when x is near c. So that's very similar to the definition we saw for absolute maximum and absolute minimum values. Here's an example. Determine the absolute and local maximum and minimums for the function y equals cosine of x. Now we see that we have some hills and valleys, but also what is the absolute maximum value of cosine? We know that to be 1. So we can see here, here, and here we have absolute maximum values. but those are also local maximums there at the top of the hill. So those are absolute maximums and local maximums. Likewise for the minimum values here, the absolute minimums, we know the minimum value of cosine is -1, but they are also local minimums. Now we have not restricted the domain of the cosine graph, so in order to determine all of the absolute and local max and mins, we can see that the absolute maximums occur at 0, at 2 pi, then at 4 pi, 6 pi, -2 pi, -4 pi. So we could say the maximums occur at 2 pi n, where n is an integer value. If n is 0, that gives us our maximum at 0. If n is 1, that gives us our maximum at 2 pi, and so on. N could be -1. So we'd have our maximum at -2 pi. And the minimums, likewise, we could identify all of those as pi plus 2 pi n. Determine any local or absolute values of x equals y equals x squared. We know this function, y equals x squared, continues infinitely, and the domain is -infinity to +infinity. So for this particular graph, we do not have an absolute maximum value. Also, we do not see any hills, so we do not have any local maximum values. Minimum values, the absolute minimum we can see occurs here at x equals 0, and the value is 0, so an absolute minimum occurs at x equals 0, and it is also a local minimum. And the value at the local minimum and absolute minimum is 0, y equals 0. Find all, if any, relative or absolute maximum and minimums of the function y equals x cubed. Now for this function, again, we're looking at the domain from -infinity to +infinity. This just continues infinitely upward and infinitely downward. So we can see that there would not be an absolute maximum value or an absolute minimum value. Looking for a local max or a local min, we don't see any of those hills or valleys, but how can we be assured we don't have a little area there that goes up, comes back down, then goes back up? In order for that to happen, we would have to have the slope of the tangent line, that would be negative. Because if we're going to go up to a hill and back down to a valley, we're going to have a negative slope in between those. Let's look at the derivative of this function. Y prime would be 3x squared. 3x squared is always positive, and at one point it equals 0. So this function is always increasing. It's increasing on the interval from -infinity to 0, and from 0 to infinity, it's increasing. So this never comes back down, so it can't create those hills and valleys. So this function does not have any local maximum or local minimums. Find the absolute and relative extreme values of this function. Now here's a graph of this function, and the domain is restricted. we are only going from -1 to 4. We are looking for any absolute and relative extremes values of this function. We can see an absolute maximum occurs here when x equals -1. This would give us an absolute maximum. Now the absolute maximum value, we could plug that value into our function to find exactly what the value is. And it appears it would be around 37, so we'll say 37. An absolute minimum occurs here at x equals 3. And that value appears to be -27. So we have an absolute minimum when x equals 3, and the absolute minimum value is -27. Looking for relative extremes, we have a valley right here, and the lowest point is there. So we have a local minimum at x equals 0. Here we have a hill, and the very top there is at x equals 1. There's a local maximum. And then at x equals 3, that again is a local minimum, as well as an absolute minimum. Now, if we wanted to find the values of our local maximum and minimum values when x equals 0, the relative minimum is 0, the relative value is 0. When x equals 1, the relative maximum value is 5. And then when x equals 3, that is a local minimum, and we said the local minimum value then would be -27. The extreme value theorem. If f is continuous on a closed interval a,b, then f attains an absolute maximum value f of c, an absolute minimum value f of d at some numbers c and d in the interval ab. So here we have a continuous function on the closed interval a to b. The extreme value theorem states there must be a maximum value on this interval, and in this case the maximum value would occur at b and the minimum value would occur at a. If we had a different function, let's say something like this. Here we can see it has an absolute maximum value at c and absolute minimum value at d. You may be thinking, what about if we have a horizontal line from a to b? We still have a maximum value. All of the values between a and b give us a maximum value. Also, all of the values between a and b give us the minimum value of the function. So a horizontal line still fits the extreme value theorem guidelines. We still have an absolute maximum and an absolute minimum value. Graphical representation of the extreme value theorem. There's our absolute maximum and our absolute minimum. Here's another example. We have a closed interval from a to b. We have an absolute maximum and we have an absolute minimum value. Determine the maximum and minimum values for this graph. thinking about the extreme value theorem, we should have an absolute maximum and an absolute minimum on the interval 0 to 2. So we can see that the absolute minimum value looks like occurs at 2. Let's look for the absolute maximum value. Now it looks like the absolute maximum would be somewhere in there. So if we chose a value, say 0.9, let x equal 0.9, and we think that's the absolute maximum value. Well, somebody's going to come and say, well, 0.99 gives me a value even closer, and that would be a y value that's larger. And we could repeat this and just keep saying, well, I'm going to add another 9, and that value would give me a y value even larger. So you can see there's not an absolute maximum value for this function. We could approach 1 from the left side infinitely, and our y values get a little larger, a little larger, a little larger. So does this break the rules for the extreme value theorem? Well, if we went back and looked at the definition, it says we can only apply the extreme value theorem if we're working with a continuous function on a closed interval. This is not a continuous function, so it does not break the extreme value theorem. Let's look at another graph. So here we are looking at an interval from 0 to, it appears about 1.8. Looks like it has an asymptote at 1.8. Let's look for our absolute minimum, absolute maximum. As we approach 1.8 from the left, we can see the function's getting larger and larger and larger. So there's no absolute maximum. And as we approach 0 from the right, we're not going to have a minimum value for the same reason we didn't have a maximum value on the last graph. So does this break the extreme value theorem? No, this one doesn't either. This one is not on a closed interval. 0 is not included, 1.8 is not included, therefore it's not on a closed interval, so it doesn't break the extreme value theorem. We don't have to have an absolute maximum and absolute minimum value. The extreme value theorem indicates that there exists a maximum and a minimum value on a closed interval, but it does not say how to find these values. We discussed this a little bit earlier, where we said we believe that the absolute maximum and minimum values on a closed interval for a continuous function are going to occur either at the endpoints or at our local maximum and or minimum values. So Fermat's theorem, if f has a local maximum or minimum at c, and if f prime of c exists, then f prime of c equals 0. Here's a function. We have some local maximums. Let's call this c sub 1. We have a local minimum at c sub 2. And if we drew the tangent lines in at those points, we can see that the slope of the tangent line at those points would be 0. So f prime of c sub 1 equals 0, and f prime of c sub 2 equals 0. This function, we saw the graph, we knew we had a local maximum and a local minimum. Therefore, we knew f prime of c would equal 0 at those points. Now let's look at the converse. If we said if f prime of c equals 0, then we have a local max or min. Is this true? Well, if we switch the hypothesis and conclusion, we can see that this is not true. We looked at an example just a few minutes ago, y equals x cubed. We saw that f prime of 0 equals 0. But is there a local maximum or local minimum at 0? No, no local max or min. And I'm going to abbreviate maximum and minimum. So we do not have a local max or min. So you can see the hypothesis, which is this here, cannot be switched with the conclusion. We can only say if f has a local maximum or minimum at c, and if f prime of c exists, then f prime of c does equal 0. Here's the example to show the counter argument if we switch the hypothesis and the conclusion. F of x equals the absolute value of x. This has its local and absolute minimum value at 0, but what value can't be found by setting f prime of x equal to 0? Because f prime of c does not exist. Remember when we talked about if we look at the graph of a function, we know it's not differentiable if it comes to a point. So we know at x equals 0, it is not differentiable. But it does have an absolute minimum value at that point. Let's look at the derivative of this function at 0. We know to find the derivative of a function, we can use the limit of the difference quotient as x approaches a. So we're looking for f prime of 0. So f prime of 0 would be f of x minus f of 0 all over x minus 0 as x approaches 0. This is the limit of f of x is our function, which is the absolute value of x, over x as x approaches 0. This limit is going to give us the value of the derivative at 0 for this function, if we can find it. However, if we built a piecewise function this function equals, we know it equals x divided by x, which is 1 when x is greater than 0, negative x divided by x when x is less than 0. So if we looked at the one-sided limits, we'd have the limit of the absolute value of x over x as x approaches 0 from the left. We would use this. And we can see that negative x divided by x is just negative 1. The limit of the absolute value of x over x as x approaches 0 from the right, we would use this function, which is x divided by x, which is 1. We can see the one-sided limits do not agree. Therefore, this limit does not exist, which indicates this derivative does not exist at 0. Now this brings up an important point, that here we have an absolute minimum at x equals 0, and that derivative does not exist. So as we were talking about earlier, we know these absolute maximum and minimum values occur either at the endpoints or where the derivative equals 0, and now we can see we have to check one more place where the derivative does not exist. So when we're checking for our local minimum and maximum values, we need to check where f prime of x equals 0 and where f prime of x does not exist. We must be careful when using Fermat's theorem. Even when f prime of c equals 0, there need not be a maximum or minimum at c. There may be an extreme value even when f prime of c does not exist, as we saw in the last example. Fermat's theorem suggests that we should start looking for extreme values of f at the numbers c, where f prime of c equals 0, or f prime of c does not exist. These numbers have a specific name. We say they are critical numbers. So here's a definition. A critical number of a function f is a number c in the domain of f such that either f prime of c equals 0 or f prime of c does not exist. That's where we're going to start looking to see if we have absolute maximum or minimum values. We'll find those critical numbers, plug those into the function, compare it with the endpoints. The value that gives us the biggest number is the absolute maximum value, and the number that gives us, the critical number that gives us the smallest number, the critical number or the endpoint that gives us the smallest number, will be our absolute minimum value. Let's try this. Find the critical number of f of x equals x to the 3/5 times 4 minus x. We know that critical numbers can be found at f prime of x equals 0 or where f prime of x does not exist. So we need to find the derivative of this function and see if there's any place the derivative does not exist. I'm going to rewrite this function. I'm going to multiply this through. So we would get 4x to the 3/5 minus, now when we multiply these together, the exponent here is 1, or 5 over 5. We would add our exponents to get x to the 8/5. Now we can find the derivative. So f prime of x equals 4 times 3/5 x. Now we're subtracting 1 or subtracting 5/5. So we'd have to the negative 2/5 power minus 8/5 x, and again we're subtracting 1, so we would end up with the 3/5 power. If we clean that up a little bit, we would get 12 in the numerator, 5 is in the denominator, and I'm going to go ahead and rewrite this x to the negative 2/5 with a positive exponent in the denominator. And then we have 8x to the 3/5 all over 5. Now let's get a common denominator. So we would have to multiply this term by x to the 2/5 over x to the 2/5. And we would get 12 minus, now when we multiply these together, we would add the exponents, and we would just get 8x all over our common denominator. So there's our derivative, f prime of x. Now this expression will equal 0 when 12 minus 8x equals 0. So if we solve for x, we would subtract 12 and then divide by negative 8. So we would get 12 over 8, which reduces by a factor of 4 down to 3/2. So there we have found a critical number, x equals 3/2. We also have to check where f prime of x does not exist. How can we make this derivative, how can we make that not exist? Well, if we plug 0 in for x in the denominator, then that is undefined and it does not exist. So here is another critical number. So we have two critical numbers, x equals 3/2 and x equals 0. Here, this example is showing using the product rule instead of multiplying through first, but you see we get the same result. If f has a local maximum or minimum at c, then c is a critical number of f. To find an absolute maximum or minimum value of a continuous function on a closed interval, it is either a local at a critical number or at an endpoint of the interval. So it's going to be at a local maximum or a local minimum or at the endpoint of an interval. That's how we're going to find our absolute maximums and absolute minimums. Next, part 2, the next video, we're going to look at the closed interval method, which helps us find these absolute maximum and minimum values of a function on a closed interval.